So I guess my first question is, when you see a problem like this, I think the most helpful thing is to realize that this part is a second degree alcohol. So if we're going to attach it, that means we can't just do S2, H2SO4. That won't work because that only works for primary alcohols. We can't do R2BH because this is only H2O. It's only primary or H2O. Does that make sense to everybody so far? So that means that the question is, if we were to attach from this side, we couldn't do that. Okay, so far, so good, everybody? So then the question is, do we make this bond or do we make this bond? I'll do a different color. Oops. Right? Because in theory, if we were thinking about retrosynthesis, and this is very similar to one of the recitation problems we did, we could either go like this, or we could go like this. So which one do you guys think is the most feasible? So this is if we do the green bond, and then this is if we do the blue bond. Totally just switched it. Sorry. There's supposed to be an extra carbon here. So does anyone have an answer for what they think would be best on which one we should make first? Which one is possible? That's my first thought, right? Like, do I have a reaction that could put this molecule here? Because that's anti-Markovnikov, right? So do I have a molecule that could be anti-Markovnikov and attach something that isn't water? No, I don't. So because of that, that means this has to be our way forward. So we have to make this part and then attach it onto here. So whenever you see an ether problem, the question is always, which part am I making and which part am I attaching? You really only have two options. You could do S2, H2SO4 or oxymercation, right? So it's like, will it rearrange and give me what I want, or will it be Markovnikov and give me what I want? Does that kind of make sense to everybody? Also, I'm sorry. I keep dropping my carbons. I'm not doing, okay. Thumbs up. Do you want me to walk through how we get this, or do you think we're good? Because going from this alkene to this is, you could do oxymercation again with water, or we could do H2SO4, right? We just need to put that an OH here, and that would give us that molecule. Yeah, we can definitely walk through it. Sorry, let me just get a new page. Okay. So our question is 1, 2, 3. How can we make this molecule? And we've already said that we're going to start here. We're going to start here and we're going to make this alcohol, right? We need this one plus that one. Oops. Wait, what did I write? Why did I do that? Right, so we've already determined, okay, so we're going to make this bond, right? So the question is, how do we make this alcohol to be able to tack this onto here. And excuse me if I misspoke before. I think I might have been looking at the top problem. Does that make sense? So if we take these two molecules, that will get us our product. Right. So now the question becomes, well, how do we make this alcohol? Does anyone have an idea for maybe how we could get to this step? Is it Markovnikov or anti-Markovnikov? That's our first question, right?
Would it be the R2BH?
Yeah, exactly. That's perfect. R2BH, water, and then H2. So I would say that when you're practicing, try to write in all the solvents. Like I think it's a good habit to build, even though if you write like R2BH, like we know what you mean, but on the test, I would try to write it in. So after we get this R2BH step, right, would get us to this alcohol. And then we could just add these two together using what reaction do you guys think? Because it's adding Markovnikov because it's adding here. So what could we possibly use? Any thoughts? Maybe guesses? Yeah, exactly. We could do oxymercation. So with this alcohol as a solvent. Does that make sense to everybody? So it's like we're taking this alcohol, we're like putting it vertical, and we're just sticking it on the top. But it's important that we figured out which bond we could do that with. So we have to the most important thing for these synthesis problems is not to get overwhelmed. You want to walk through super systematically. Which bond do I make? Which bond should I start with? Don't get intimidated by a long carbon chain, right? Because we know how to add carbons. But when we see an oxygen in the middle, that's what our focus should be. How could I attach this oxygen? Is it from this side or is it from this side? Okay. Does that make sense to anybody? Any last questions?
Throw questions in the chat as they come up. How would people feel about going through a guided version of a little bit of a more complicated synthesis problem? It's super scaffolded and it's an old problem from when I took the class. Do you think it would be helpful to do that? All right, let's do it. I'll share my screen then. I also just put this in the Google Drive folder so we can all work through it. And then you can come back to it because it's this strategy is so useful for every problem you do. And I've just added a few more box problems to that Drive folder as well. And I will resend the link if anyone needs it. All right. All right, so Victoria is going to be monitoring the chat because I can't really see it while I share my screen. But yeah, let's get started with looking at how we're going to turn this propene molecule into this thing that has both an ether and an aldehyde. So the first thing we want to do is count our carbons, right? Because how many carbons are we starting with? How many carbons are we ending with? Are we making new bonds? Are we breaking new bonds? Where are carbons coming from? Where are they going? So
would you mind dropping the link to this again?
Yeah, no problem. Sorry, give me a second. Odds that I accidentally DM'd the link to someone instead of sending it to everyone are also really high. So, okay. Thank you for sending that. Okay, now that is sent for me, and I'm gonna erase that mark. And I'm trying to figure out how to count carbons because my little annotation, but there we go. Okay, so in my starting material, I have 3 carbons. In my product, I have 1, 2, 3, 4 carbons. So that means I need to add 1 carbon. Do I know any FGIs? And then technically 5 for the extra methoxy carbon. So let's just step through this instead of me asking you too many questions. So we have 3 carbons in the starting material, 4 carbons in the product plus the methoxy carbon. So that means we are adding just 1 carbon. So let's keep that in mind. Start thinking about what reactions we know to add carbons, and if we know any reactions where we can add just 1 carbon at a time. Step 2 is recounting your carbons, because counting your carbons is really important, because if you don't count them and recount them, they're going to disappear on you, and it's really frustrating. So 1, 2, 3, 1, 2, 3, 4 plus the methoxy carbon. So now we want to try to number the same carbons in both the starting material and the product. This is a little tricky because, how do you recognize these things? And it's okay to have no idea what's going on with this. It's just something we want to keep in mind when we're starting out with synthesis, that even if we can't necessarily look at a starting material and product and say, this carbon goes here, this carbon goes there, and so on, we want to say, well, I'm working with carbon 4 right now. What carbon could that have come from in my starting material? Did carbon 1 turn into what I'm calling carbon 4 or something? Or is there no way carbon 4 could have come from this original material, and that has to be the carbon I add? So I'm not going to run through it right now because I don't want to confuse you, but we're just going to keep what carbon came from where in mind as we step through this. And also this step 3, it's really great to do if you can do it, but there are a ton of problems that I look at it and I'm I have no idea. It's totally fine if you can't get through this step. It's more of just a framework to work with. All right. So now let's start thinking about our FGIs and what reactions we could use to get them there. So we are going to find 2 functional group patterns in the product that were not present in the starting material, and possible reactions we can use to form these functional group patterns. So what's a functional group in the product that we didn't have in the starting material? You can unmute yourself or put it in the chat.
Aldehyde.
Yeah, so we are making an aldehyde. What reactions do we know that can make an aldehyde?
Is it the hydration of alkyne?
Hydration of an alkyne? Hydroboration of an alkyne, specifically? Oh,
Yeah,
hydroboration.
it's not the one where you add R2BH and OH.
Yeah, exactly. So hydroboration of an alkyne, right? Because that's going to be our anti-Markovnikov regiochemistry, going to put our keto or our carbonyl group on our less substituted carbon, which is going to be the only way we can get an aldehyde instead of a ketone. Any other reactions where we can make an aldehyde?
I would have said ozonolysis, but I'm not really sure whether we're gonna do that here just because of the number of carbons.
Yeah, that's okay not to know whether or not we would do it. That's a great thought to have, so we'll keep ozonolysis in mind. That's one of our most common ways to make an aldehyde. Keep wanting to say alkene for some reason. All right, and what is another functional group that we're seeing in the product but not the starting material?
The ether.
Yeah, exactly. So we're getting an ether. And so what reactions do we know that could make an ether?
hydration, like either using oxymercuration or hydroboration first.
Yeah, so oxymercuration is a great one. That's a really good way to make an ether. Hydroboration, right, that one's actually not going to make an ether. It's only ever going to give us alcohol no matter what reagents we use. So we can like try to throw carbons in there, but really it's really like a process of protonation and deprotonation, and the alcohol is attacking the empty boron and then ultimately always kicking out whatever is attached to the oxygen. So we can never make an ether. We always just end up making an alcohol. And I'm happy to go through that mechanism later if that's something people are confused on. Any other ways we can make an ether?
We could make a halo ether too.
Mm-hmm. And then last one isn't as useful because it's pretty redundant with oxymercuration and just a worse reaction, but we can do acid catalyzed hydration. Right, make that less ugly. Okay, so now let's start thinking retrosynthetically. So we just talked about this. We know two ways to form aldehydes, so we can make a terminal alkyne, or as Stephanie said, we can do some ozonolysis. So let's try drawing the alkyne precursor from which the aldehyde could have been formed. So we're going to draw the last step before the product, assuming that we are working with a terminal alkyne to make this aldehyde. So that means that carbons 3 and 4 are going to be in my alkyne. And carbon 4 is the carbon that ends up getting attached to the carbonyl group. So that's going to be the terminal side of my alkyne. And then carbon 3 has to be attached to carbon 2 and carbon 1. And carbon 2 is going to be attached to my methoxy group. All right, that's great. So now we have this thing, and let's look at this precursor. So I have 4 carbons, that's great. And I have this alkyne. So imagine I was trying to make this whole alkyne. How many so I would be adding carbons 3 and 4 with the alkyne, right? That would be my alkyne anion. And then I would have to be adding that alkyne anion to something that's 2 carbons, right? It would be adding something to some like haloalkane or something that is like carbon 1 and carbon 2. How many carbons do I have in my starting material? 3. That's not going to work, right? Because I have to add 2 carbons at once if I am using a terminal alkyne. And so that means that I couldn't add to a 3 carbon thing because I'd end up with 5 carbons. So that means that this method of going straight from a terminal alkyne to an aldehyde isn't going to work because I can't get a 4 carbon terminal alkyne with a 3 carbon starting material. Does that make sense? Okay. Drop questions in the chat or unmute yourself if you have them. But that means, so if we're thinking about alkynes and everything, that means we pretty much have to add 2 carbons at a time, right? So if I'm adding 2 carbons at a time, that means that if I'm starting with a 3 carbon starting material and I'm adding 2 carbons, I'm gonna end up getting a 5 carbon thing. That means I have to break a carbon-carbon bond to go from 5 carbons to 4 carbons. So that just supports my idea that I know that it didn't work to use a terminal alkyne to make an aldehyde, so that suggests ozonolysis. Ozonolysis makes a lot more sense now that we know we have to break a carbon-carbon bond, because that's the only way we know to break a carbon-carbon bond. Any questions so far? Okay, so I know it's 7. Feel free to head out if you need to. We will not be offended at all. If it would be helpful for me to keep going, I'm happy to do that. The next page really just focuses on the retrosynthesis in this problem. All right. So let's go ahead and do the first retrosynthetic step, hoping that my computer doesn't die. So if we're using ozonolysis, that means that we have to have an alkene, right? So that means we're like cutting the alkene in half and getting an aldehyde and a ketone, or an aldehyde and an aldehyde. So lots of options here, but I'm just going to choose the simplest one that will contain an alkene. Something like this, right? So my ozonolysis, my double bond scissors comes in here and gives me an aldehyde. All right. So now we need to make an alkene. So we only know one way to form an alkene, right? And that is through reducing an alkyne. And I'll go ahead and write my reagents in too. All right, so intermediate A, my last intermediate is my alkene. And I am going to make this from an alkyne. And let's say I'll use like Lindlar's catalyst to make this, because it is a terminal alkene and alkyne, so we don't care too much about cis or trans. All right, so now we have this alkyne. How are we going to make this alkyne? Well, we originally had some like 3-carbon thing, and we know that we added our 2 carbons when we added our alkyne. So we know that we are kind of like adding an alkyne here, right? And so what type of reaction are we doing when we're adding an alkyne? It's an SN2 reaction, right? So we need something that's going to be a good electrophile. Normally that's a haloalkane. Well, earlier we talked about how you can make a haloether, right? So you can have like OMe on one carbon and Br, or another halogen, on the other carbon. Well, if you have Br or another halogen on that other carbon, that makes that carbon electrophilic. That means our alkyne anion can come in and do an SN2 reaction there to make our new carbon-carbon bond. And that's great, and that works really well in a haloether, right? Because this OMe doesn't really do anything. It's just oxygen attached to a couple carbons. It can't do acid base or anything. You would have a problem if this was an alcohol. But this works out nicely because we have O, E, and Br, right? So if I react this haloether with my deprotonated alkyne, the alkyne comes and attacks this carbon right here and kicks out the bromine, and we make our new carbon-carbon bond. Then we have our new carbon-carbon bond. We can make an alkene by reducing the alkyne. Once we have an alkene, we can cut one of those carbons off and get ourselves an aldehyde. All right, so finally, we just need to make intermediate C from our starting material. This is great because intermediate C just has 1, 2, 3 carbons. So with only 3 carbons, we know our starting material has only 3 carbons. So we just need to do one reaction to get ourselves there, and that is going to be adding Br2 in MEOH. And then you can go ahead and write the synthesis forward after you finished your retrosynthesis for this. but I'm not going to do that because my computer's at 3% and it is 7:06. So I can stick around for a few minutes if you have any questions and if I can find an outlet in here. But I'm going to go ahead and stop sharing. Again, this problem is in the Google Drive and I will send that link again.
Feel free to like email or reach out if you guys do have any questions.
And we're doing recitations this week as like Q&A sessions, so feel free to drop in to anyone that works for you.
I had a quick question. So whenever we want to add, like an alkyne, like we want to make sure that there's an alkyne attached to something else. Is it always necessary? Actually, no, I know it's always necessary. How do we figure out whether or not, like, because for the problems I've been doing, it always looks like we have to, like if you want to add, if you want to make an ether group or something at the end that's like attached, like a very long group that has an ether, we have to end up using an alkyne with like a kind of halo ether. And I was just like I was honestly confused as to like how we can think of a way to always break down the molecule in the best way that's time efficient, like not thinking about every single thing, but like the best way to acquire intuition about these kind of problems.
I think in terms of intuition, it's super, super helpful to just do more problems. And also like do box problems. Now that you've kind of started doing synthesis, it can be really helpful to go back to box problems and think about them in terms of synthesis. I uploaded a few box problems in the drive that are a little more like on the empty side of things. So they can really help you think about like the synthesis process without like feeling like you're doing synthesis without necessarily knowing anything. Yeah, I think that will be helpful. And I think like also like making lists of common mistakes and common patterns will be helpful with that too.
Okay, thank you.
You're welcome. Bye-bye.